for being here. Good morning for some, happy lunch for others. And so I'm going to present some work on generating and improving flow forecasts for optimization of control operations. And this talk is meant to be informative for both sides, hydrologists and control operators, by presenting a case study, and I'm going to emphasize some area that needs future work. So before, I'm just going to present the way we provide forecasts for reservoir operation. It all starts very simply with weather forecasts, and we transfer some information. The weather forecasts are transferred to hydrology models, and the data that are being transferred are usually temperature, precipitation, potential evapotranspiration, wind. Those are spatially distributed data, and they force, in my case, a hydrologic, and we create hydrology forecasts. The hydrology forecasts are streamflow forecasts. Times at start, they are time series, and they can also be presented in different formats. For example, when it's an ensemble, it's a chance that an event is going to happen. And so those forecasts have different scales for different products and over different time scales. But what is being provided to the reservoir operation optimizer here usually are time series. And the reservoir operations have big work to do because they do need to combine the hydrology forecasts that have different scales over different time scales, and they need to, as an input, as a porting, they also have the demand forecast from the different stakeholders. So here we have, for example, hydropower, irrigation, flood control, recreation, environment, and others. And all of them have competing objectives over different time scales, and they have different priorities. So that's a lot to combine to minimize the cost and optimize the water delivery. So usually the optimizer are taking the hydrology forecast time series as is. And so I was wondering, the question I had was, how are hydrological forecasts used for reservoir operation optimization? Look at a very simple question. What I mean by that was, in case of seasonal forecast, for example, part of the hydrological forecast is actual forecast, while the other part, at the end of the water year, it becomes climatology. So it's not forecast. You know, in one sense, this is non-information. So this is not forecast, but it's going to be the same every year. So what is the contribution of the actual forecast to the improvement of reservoir operation, or the one that is going to make a difference? And there are different formats for the hydrology forecast with the different skills. As I mentioned, over the time series, there is different skill over different time horizons, but there are also the probabilistic forecast where you're going to have a distribution, or you're going to derive statistics over certain events, and it might be more skillful for one event than another. So how is that skillful part of the forecast being used by the optimizer? Is it being used, or is it being used by the forecaster? How does it all fit together? And in order to address those questions, I want to go through a case study. And the case study starts with a context example. Usually, for field forecast, you can have the National Weather Service providing for forecast to the Bureau of Reclamation, to the Corps of Engineers, who are going to optimize releases. When you go to smaller facilities, it can be a little bit more integrated, and some industries are going to private companies to provide the hydrology forecast, for example. And in my case, the Department of Energy has been developing a water use optimization toolset that I'm going to present, and this is an integration of the different components, hydrology, flow forecast, and optimizers. So that's the context, and then I will go into presenting the hydrological forecast tool that is part of this toolset. And at the same time present the steps that are done to generate the best possible hydrometeorological forecast to force an optimizer. And I will go then through an application of the Feather River Basin. What I want to achieve here is just give an example of the hydrological forecast that we provide to the optimizer, how we verify them, and I'm going to finish with, okay, we provided those hydrological forecasts with a certain skill. How was this skill transferred to the reservoir operations? How were those hydrological forecasts used? So first, I'm going into the context, the background. It's the Water Use Optimization Toolset. As mentioned in the introduction, we have a challenge, which is to operate for the Department of Energy, the conventional hydropower plants, in an increasingly uncertain and competitive water-constrained environment. We have complex electricity markets that are at 5-minute time step, and we have environmental constraints that are very much longer horizons, and then we have water supply, demand, and restrictions. So what the toolset wants to achieve is to link the water supply, the water generation, the ancillary services, and environmental performance at once, so that we can better use the energy and the grid services from the available water while preserving or improving the environmental benefits. The way it works, it's a combination of different national labs. We have Argonne National Lab, Oak Ridge, Pacific Northwest, and Sandia. And the toolset is then has 4 components that is being led by each of those national labs. And the hydrological forecasts are providing products to the seasonal the seasonal optimizer, the seasonal operations, which is starting with a day-ahead short-term reservoir optimization. And they both interact with an environmental performance so that there is, we're looking at the environmental flows and fish so that we have the best compromise between the competing objectives. The way it works in different pictures is so PNNL is the lead for the hydroclimatic forecast, so providing the internal forecast to Sandia National Lab with leading the development of the seasonal reservoir operations. And this is not only releases, but there is a water quality component. And they work with GEARS, which is the day-ahead scheduling real-time operations. So they are being provided a range of a reservoir, a range of volumes that they can play with for sub-daily releases for hydropower. And they all work with the index of river functionality, which is being developed by Argonne and Oak Ridge. And so that there are metrics that needs to be maximized. So that's how we then can make decisions to release water for hydropower. So as part of this, I'm part of the hydrologic forecasting tool team. The lead PI is Mark Mosta from PNNL. And so I'd like to acknowledge the co-authors. We have Andrew Coleman, Rick Skaggs from PNNL, and this is also a collaboration with Mark Nyson and Dennis Littenmeyer from the University of Washington. And as part of the requirements from the toolset, we need to provide not only Streamflow forecasts, but also meteorological forecasts at multiple user-defined temporal and spatial scales. So for this, we're using a physics-based distributed hydrology model so that we can create new flow forecast points. And this is even more important for the environmental component because they need natural flow forecasts at a couple of places to derive the environmental metrics. Because it's a tool set that needs to be flexible and easily used, we need to have a consistent national approach. We are using an automatic assimilation of spatial and temporal data Here we're trying to reduce the need of a forecaster because it's an independent toolset, and this can be discussed later. And the product that we give is ensembles that can inform on probabilistic risk assessment. But what are the steps that are being done to provide the best hydrometeorological forecast to our partners? So here I'm just filling the blank between the weather forecast that I had at the start and the hydrology forecast, which is the output. So we start with the weather forecast. They are being pre-processed. The reason there is a preprocessor is that we need to have the weather forecast unbiased. And we also calibrate the probabilistic information in the weather forecast. Based on this, we do now have new ensemble meteorological forecasts that we can start providing to our to the seasonal component. And with the hydrology model, we then provide ensemble flow forecasts that we can keep improving with data assimilation of snow water equivalent or river flow observation in real time. But here again, there might be bias with respect to the real-time observed flow. So there is a post-processor that comes into place right here that is supposed to correct some remaining biases and keep calibrating the probabilistic information in the ensemble, especially as usually for very short lead time, the ensemble is too narrow because it's driven by initial conditions. So it needs to be widened, and so we refer it hereafter to it as the calibration of the forecast. So once we have our flow forecast, before we can provide them to the user, here this is our seasonal component, for example, but we do a flow forecast verification. So the flow forecast verification is you do perform a retrospective data set, and you want to assess what is the actual scale of your forecast. And so that then you can provide additional information to your user, saying, oh, over that period or this aggregated period, this is the scale we have. And hopefully we think this information is going to be used by the user. This is, we're still in the technical approach section, and this is just giving a different perspective on how we do the hydrologic forecast. And we've been leveraging from the University of Washington West-wide seasonal forecast system developed by Andy Wood and Dennis Meyer in 2006. And the way we do hydrologic forecast is there is an important component driven by initial conditions. So the accuracy of the forecast is to some extent dependent on the quality of how we derive the initial conditions and how well we simulated the past. So we have a spin-up of the hydrology model. So it means that we force the hydrology model with near real-time and real-time observed meteorology. From this, we are creating an initial state of the hydrology of the basin, meaning that we have a certain amount in the snowpack, and we have a certain amount as a soil moisture. From this, we further force the hydrology model with ensemble seasonal forecast. There is an approach called ESP, ensemble streamflow prediction, where especially for snow not control basins, the different traces of the different forecast traces are in fact a something from the past. And it means that we think there is little information in the climate, and the forecast is mostly driven by initial conditions. So this is the seasonal forecast that we are actually using in the system, and this is widely used in the Western US as well. But given the requirements of the toolset, we saw that we not only need seasonal forecasts, but also we need some skill at shorter time scales. So what we did here is that we augmented that system with first medium range forecasts. They are based from GFS forecasts, so it's a global forecast system, and those are 14 days long, There are 15 members, and we do pre-process them the way that I described in the previous slide, so that those forecasts are unbiased with respect to the nowcast data set, so that we have a consistent flow forecast. What we do too is we added a river flow assimilation. The goal of this one is at the time of the forecast, there might be a bias between our near real-time flow simulation and the observed flow. So in order to fill that gap and make it unbiased, we use the river flow assimilation approach. And during summertime, it will also improve longer-term forecasts. While here for SWE, the snow water equivalent, it has some application at longer-term timescale and also medium range during snowmelt periods. And then one last thing is, because we now look at shorter timescale, the improvement that we can see from data assimilation is going to pick up just a couple days after the assimilation, and that time is the time of concentration of the basin. So in order to have improved forecast from day 0, we do perform the assimilation a couple days before the actual forecast. So now you know everything about hydrological forecast and how can be generated. I'm not going to talk about the data assimilation here, but this is the kind of research that is being done to keep improving the ensemble for forecast so that we can provide them to the user. So what we have to do now is to go into a case study so that we can explain the different hydrological forecast products that we got out of that system. So presently, the toolset has 3 demonstration basins, and we're going to a 4th one. The first one is the Oroville Thermalito Complex over the Feather River Basin in the Sierra Nevada in California. Our partner over there is the California Department of Water Resources. It's the rain-snow transition basin with wet winter and dry summer. We have another basin that is the Kennington River Basin. This is the hydropower facility, is the Espinal unit, and our partner is the Western Power Association, and this basin is snowmelt control. And then we have the Conowingo Dam over the Susquehanna River Basin, and our partner is Excellent Power Corporation, and this is rain-snow transition basin, but it's a wet winter and wet summer. And we're getting a 4th basin here in Seattle. It's the Skagit River on the western coast of the Cascades, and our partner is Seattle City Light. So here my case study is actually going to be on the Feather River Basin. This basin is about 8,000 square miles. It rains from November to March. And this is rain-snow transition. About 40% of the snowmelt, of the snow contribute to the annual flow. And there is then the Oroville Reservoir at the output of the upper basin. And the primary operation is for water supply, flood control, and irrigation. And secondary uses is recreation and hydropower. Hydropower generation capacity is 760 megawatts at the, between the Oroville Reservoir and the downstream facilities of Thermalito. And just to give you a reference, nuclear reactor is about 800 to 900 megawatts at full capacity. So this is pretty significant here. So based on our system we saw before, once we have the basin, we need to set up the hydrology basin on that, the hydrology model on that basin. So here we did a calibration at the daily time scale. And the flow hydrograph that we get after our calibration is in that panel. We have the black is the observed naturalized flow, and in red this is our simulated flow. We're using the big model, and we have an annual bias of 0 over the validation period, a daily national efficiency of 93%, and a daily correlation of 0.84. So 2 things to see here. First, it's this is a pretty good calibration Number two, this is still correspond to the bias that we have, and so that will be, this is our best forecast, and this corresponds to the bias that we have when we're providing hydrology forecast to the optimizer. So from this, we've been generating full forecast. The seasonal forecast, this is just to give you an example. We're providing a time series, a daily time scale, 12 months long, 50 ensemble members. And just to give you an example, this is a forecast issued on April 1st. And the black is the observation, the red is the ensemble forecast, and the blue is our best forecast. By best forecast, I mean that we are forcing the hydrology model with the observed meteorology. So if this is the best weather, the perfect weather forecast, so that will be our best flow forecast, the best that our hydrology model can do with modeling errors, etc. And this is the red is in forecast mode. For the medium range, we have a 14-day time series, and it's a spaghetti plot. So we are providing those spaghetti time series and the associated meteorological forcing to our optimizer. But as we are providing them, I mentioned that we are also checking on the skill of those forecasts. So first here I'm going into the forecast verification of the seasonal forecast, and those are driven by initial conditions. There are different skills that we are looking at: the mean errors, predictability, and reliability. And in this case here, I'm showing the correlation, the predictability of our monthly flow forecast. For forecast issued in April, with the lead time here at month 1, 2, 3, 4, and you see that there is a good correlation from April to about July, August, and this is standard for this kind of ESP approach. The skill, where there is the month of the skill, is from April to July, and the product that is being given is April to July volumetric forecast. After this, after April, July, this is climatology. This is once you reach the end of the water year, this is the same every year. So this is what I was mentioning at the beginning. It means that we are providing forecasts that have a skill for April to July volume, and then it's always the same. So it's forecast, but it's really the same information every year. So as we are providing a time series of 1 year long to the optimizer, we're also providing another kind of product, the skillful product, with the April-July volumetric forecast. And just to give an example, here this is the probabilistic information. This was actually for the Gunnison, but in blue was the one provided by the River Forecast Center. And in red, this is those were our forecasts. And we see that we have a bias because we are lower all the time, but the probabilistic content is the same. Let me just walk you through here. What it means is that we have 50 ensemble members, so we can derive statistics. And for example, here, it means that there is the 10% chance that a certain flow is going to be exceeded. And here it's a 90% chance that this flow is going to be exceeded, and we have the minimum and maximum flow. So this is, unfortunately, not necessarily what is going into the optimizer, but this is what we are giving. This is the extra information. We do forecast verification for medium range as well. I need to hurry up a little bit. So we have the mean errors, predictability, and reliability. We are looking at a little bit more metrics for those medium range forecasts. We are looking at different accumulated values, and we are looking at different flow categories, high and flows. And here for the upper decile, the high flow category, we're showing here only the correlation, meaning that we have skill over the first couple of days, but then it decreases, and persistence being usually a good reference for short-term time scale. We need to be persistent when we do. And this is just, those are rank histograms, and when they're flat, it means that the probabilistic information is reliable, and when it's U-shaped, it means that this is overconfident. So here, before the post-processor, the ensemble is too narrow at first, but then we have a good information. So you see that for different time scales, we have a different skill from our forecast. we are going to have a better predictability over the first couple of days, but we are going to have a better reliability in the probabilities after a couple of days. So depending on what the optimizer is going to look for, there will be more or less skill at different time scales. So we've seen the data and the product that we're providing to the users. So what I wanted to go into next was, okay, how is it being used by the optimizer? So this is work that has been done by Daniela Anguilleri. She's a PhD student with Andrea Castelletti and Francesca Canosi at the University of Milano, and Bob Nyson and Dennis Lettenmeyer at the University of Washington have been providing support as well. So what we've been doing here, this is outside of the toolset now. We created a reservoir system for the Oroville Reservoir. We made it simple, and what we did is we created an optimizer. It's a deterministic dynamic programming where the objective function is to minimize the square of the supply deficit, and the constraint is flood control. So here in the objective functions, you have a longer term. It's an objective over a long period, while the constraint is more on the medium range to short range side. And we have been training, optimizing the releases based on observed flow, which are the perfect forecast. And then we are optimizing the water delivery for diversion, for irrigation, domestic supply, and environmental needs, and the delta from the Sacramento San Joaquin Delta that were provided to us from California. So we validated that system by looking at that we were meeting the delivery, the demand, and we were also looking at the historical storage. We did a couple choices here where we took the top conservation storage, the most conservative rule curve, and we see that we do reproduce the historical storage. So in brief, we now have a simplified reservoir system for the Oroville Reservoir, the Feather River Basin. And we are right here on the top left. We just saw what was the case with the perfect forecast. Now we look at a different experiment. What if now we put it, we force and we train the optimizer with the best forecast, meaning we force the hydrology model with observed weather, and this is going to be our best simulated flow. And we look at the delivery and how we meet them, or what is the supply deficit. This is our best forecast case, and the difference in cost in the objective function, meaning the supply deficit, the square of the supply deficit, is giving us an idea of how much the forcing and modeling errors impact the system. Now we're looking at the climatology case, meaning that we are forcing the optimizer with climatology, meaning long-term means monthly flow. So there is no skill in climate and no skill in the initial conditions. More or less the worst forecast we could get them, although there is value, but here in our test, those are going to be our bounding values, our best case and our worst case. And when we use our seasonal forecast, remember it's we force the hydrology model with ESP, and then we have the water delivery, we have the skill in initial conditions, but we have none in climate. So the difference in cost between those two experiments, climatology and ESP, is giving us the value of the forecast driven by initial conditions. And the difference between the best forecast and ESP, the difference is no skill in climate but skill in initial conditions, while here there is skill in initial conditions and perfect knowledge of climate. So the difference in cost is giving us the remaining forecast skills that need to be gained. That's the information that we could get by having better knowledge of the climate. So our period of study here is from 2000 to 2010. We have 11 years. This is the inflow, annual inflow over those 11 years. And we're showing the maximum reservoir storage, and we see that 5 years out of 11, we had inflow not filling the reservoirs. So what happened with our optimizers and our different experiments? But first, so we're looking here at the cost of the objective function. So this is the square of the supply deficit. The blue is the perfect forecast. The red is the best forecast. Purple is ESP, and orange is the climatology. So we had some years where we could not meet the demand, but just to give you a perspective here for the climatology, they represent about 2% of the inflows that here we couldn't meet. And what you can see here too is that because we have dry year in 2001, what happened to the optimizer is that they incurred some cost the year before because they had the full knowledge of the climate for the next entire year. So it knew that next year would be dry. So in order to minimize the square of the deficit, they incurred some cost here to have a lower cost on the year after. And this happens again in 2007. So that's what brings you with the knowledge of future year climate, is that you can, because of the way the objective function is written, this is what we got. So then we look at the value of forecast in the different ways. That is pretty standard. Is looking at each miss and false alarm. So in the first two rows, we have the validation of the ESP with respect to the perfect forecast. So this is error in the modeling errors and no knowledge of the forecast, but we have the no knowledge of climate, but we do have knowledge in the initial conditions. And here, this is the climatology forecast. There are 5 hits, 1 missed, and 1 false alarm. Now, when we compare it with respect to the best forecast, so they have the same hydrological errors. Now we have 6 hits, 2 misses, and 0 false alarms. So it seems that we have not really any added values between ESP and climatology, but let's look at the total cost and average cost per event. Here I'm looking at the supply deficit square again over the entire period, but I'm looking at the total cost. What I see here is that the difference between the blue and the red is the cost of the modeling errors. From red to purple, this is the cost of no knowledge in climate. So with research in climate forecast, it means that we need to come from here to here. We need to fill that gap. And between the yellow and the purple, we have the difference in the initial conditions. So this is the impact of the knowledge of the initial conditions until the end of the water year, because then everything gets reset. And the cost is really during the heat. And what we have is a 12% lower cost when you're using ESP instead of climatology. So it's a different way to look at the value of the forecast. When I look at the average cost per event, I also have a 12% lower cost. So how are hydrological forecasts being used? They're being used as time series. For this particular system of the ROV reservoir with the objective functions, the way we wrote it, there is a significant value of the interannual flow forecast, which is climatology, which means that we know that there is skill in our seasonal forecast, but we know that most of the skill is only from April to July. But the optimizer needs to use it for 1 year long, and some of the skill is kind of being drawn by the standard, the known information in the climatology. So what we have here is the role of the forecaster, which need to decide on the flood control operating rules and the rollover storage based on the skillful part of the forecast. That is the April-July volumetric part, and this is the isolated skillful part of the forecast that the hydrologist forecaster provide to the decision maker for the to the operators. So there are 2 products that we provide. There is a time series, but there is also this knowledge of our forecast that we need to provide to the decision maker so that they can also have an information. So the ongoing work that we have here is that we need to generalize findings for different reservoir applications so that the skillful part of the forecast will have different impact on the cost of the objective functions, but this will differ for different reservoir and catchment characteristics. And we need to identify the level of accuracy and the period that contributes the value of the forecast. What I want to conclude here is, in my opinion, the added value of the hydrological forecast as seen by an optimizer can be misleading. And another way to look at it is through the way that the hydrologic forecasts are being done, when we know that there will be no information in the seasonal forecast, we base our forecast on the initial conditions. We also combine forecasts with different skills across different horizons. We combine medium range, monthly, and seasonal forecasts from different sources so that we're going to have the best skill over different timescales. And based on information given by meteorologists, we also filter traces for ENSO, El Nino, and different oscillations. That's the way that we improve our forecast. In terms of reservoir operations, we've been providing time series. The isolated, skillful part of the hydrological forecast seems to be taken into account by the human decision maker, but not as much as we would like by the optimizer. And this is the part where I think we need to have research. And that will conclude by then addressing some of the questions from the start. How to improve flow forecast for improved operations. So even if the optimizer says that there is not all that value, well, we do need the entire system. We need the preprocessor, we need data assimilation, we need the post-processor. But what we also need to know as hydrologists, we need to know the reservoir operation optimization scheme. If we don't know how it works, we can't improve the inputs. So we need to know what is more important, the bias. Is it more important than correlation? And this question is all the more important that we're going to ensemble forecast where we have a probabilistic product. And there are ways to tune the operating rules so that they can go in steps. We know we have the skill, a good skill in, say there's a 50% chance that this event is not going to be exceeded, then what will be the appropriate operating rule? Oops. And we need to know the weight between the different variables to be minimized. We need to know if the objectives are going to be constants or objective functions. So we need a tight collaboration between the reservoir operators and the forecasters. And with this, we'll end it with thanking the audience. I also would like to thank the Department of Energy, who's been providing the support for the water use optimization toolset. Mark Mosta, the lead PI for the Hydrologic forecast tool of the toolset. California Department of Water Resources, who helped us set up the reservoir system for Oroville in a simplified way. And Cindy Workluster will help me clarify that presentation. Thank you.
Okay, thank you very much, Nathalie. So we now have questions from the audience. You can either speak, if you can unmute yourself and talk, or you can also give questions to the chat if you cannot. So please go ahead with questions.
Hello, Nathalie. Can you hear me? It's Jan speaking.
Hi.
Hi. I'm not sure yet about the question, but I came in later, halfway of your presentation, but at least to thank you for the presentation and to say that for me it's very interesting to see work on reservoir control, reservoir optimization in relation with the ensemble forecast. And just one much more general question is I just come from an MSc research project defense here at IHC, and I was immediately wondering if the results or the tools or forecasts used in your projects, if they would be maybe available also for research students or not, because it's related to this reservoir operation agencies.
Thanks for asking. Yes, so that's a good question, and this is why in the second part of the talk we built a different optimizer. So the forecast, like the retrospective data set that we created, I believe is available for research products.
Yeah. Okay. Exactly.
Not in real time.
Yeah. Yes. You. That's where you recreated the operation, the rule curves, and the operation basically.
Yes. So everything that
model,
is upstream of the reservoir system, it's available. It's a research product. But yes, the output from the system. Well, here this is a research project. When looking at the value, so yes, we're going to write a paper with Daniela on this. But the output from the tool set itself, this is a different story. This is private.
Yeah, I understand. Okay.
But we can talk offline too. Let me know what you need.
Yeah, no, but it's indeed already. Yes, would be interesting to see for even the optimization you built, so to reproduce the data, and that would already be interesting. Yeah. Well, we have to talk. We can talk indeed later, maybe more. Yeah.
And exactly that's the point, is that those results will be different for different type of optimization. And if both forecasters and operators know about each other product and how they work, we still need to know from the operators, when they take the forecast, what metrics are they looking at, if they verify themselves the forecast they have used, and what is the degree of accuracy they need on the different metrics. What is the target, so that we are getting the best forecast for optimizing those operations. So this is this communication part that I want to go more into.
Okay, yes. So that you can still do in a follow-up. You can discuss more with them. Did you see in the data that did they do unexpected things? So did you?
Well, we haven't. Here are things. Let me get out on this. We haven't compared our the exact operations with ours. We've been mostly comparing the reservoir status, which is giving us an idea, because we're using also the observed inflow and we have the right storage. So there was going to be we have information on what was the releases, but yes, there are always last minute things that there are some differences in the operations that we were not able to do because we do not have the forecaster role.
Yeah. Thank you. Thank you very much.
Thank you.
Thank you. Do we have any more questions? I'd like to follow up a bit on Sharkan's question there as well on the data. How willing are these companies to share the data? I mean, now you showed some examples, but in general, how easy can you get them to share the data with you?
Well, we have an agreement because it's it's business sensitive. So we're marketing hydropower. So here, as we are building the toolset, there is one part that providing the forecast as a retrospective data set is something that is more available. That's what's happening then through the optimization and the ancillary services. So each of those components, hydroscope and tiers and the index of river functionality, each of those tools have been the subject of publication. So this is the part that is, every time you go into the publication, then the data are available. Once you bring them together, then it becomes business sensitive. So it's probably, if you want to go and have,
If I may, I have another question, if possible.
Mm-hmm.
You have this slide where you have the, let's say, 4 boxes with the climatology information, the perfect forecast, the best forecast. Yes, this one. So this is a great setup to compare indeed the values of the forecast and maybe even forecast components. I'm thinking that maybe you did it already. Would it be interesting to take out components of the whole forecasting sequence, and then to see how this forecast or the value of the forecast changes? So, for instance, if you would take out data assimilation that you have, snow cover.
Yes, that's part of the research. Exactly. Trying to give a quantified skill over different periods, and then knowing by what will be the added value. So here what I didn't show was once we add the data assimilation to the ESP forecast, what is the decreased cost?
Yeah, exactly. Yeah.
But the thing here is, I didn't show it here, but for example, for the snow, it was improving the April to July value, so it was decreasing the cost, but we were still missing the skill in the climate. So we are still missing, it was not improving by as much as we would have thought. And that's because of the value of the post-water year climate, the climatology. So what we want to do now is really see, so we know that this is the skill, the non-skill of the climate, a little bit from still improving the initial conditions, but what are the period of skill it needs? So does it need April to July, but if we are going April to August, what would we get if we had skillful forecast 0 from April to July, but then we had perfect knowledge from August to the end of the forecast, past the water year, how much would we win? That's exactly what we're trying to go next, is identify the level of accuracy and period that contribute the most to the value of the forecast.
Yeah.
And we need to also know that this is for that system, for that types of reservoir, for that types of users, but then we're going to go further and see for different reservoir capacities, would it be the same? If we were changing the objective functions, then we were going to instead of looking at the square, we're looking at the cubic cube of the supply deficit. How much will we get? It gets pretty complex.
Yeah, yeah, but it's a very nice research setup where you can indeed play a lot with all these components and immediately quantify the effect. Yeah.
Thank you.
Nice.
Hi, Nathalie. This is Shi from Princeton University.
Hi.
Hi, let's talk. I just have a question. So you incorporate the GFS medium range forecast into the ESP seasonal forecast system, right?
Yes.
So I'm wondering, so have you done any comparison between these two, like compare this with the regional ESP forecast? Because for the ESP, in the first few weeks, we may expect that image condition may have a strong control. And I'm wondering, so how big the improvement by incorporating those GFS short-term forecasts?
By regional ESP, do you mean kind of a seasonal forecast, like GFS?
Like ESP, yeah.
Like ESP?
That ESP without the GFS forecast.
Oh, yes. Well, actually, the way that what matters, the fact is that the medium range forecast was helping with the flood control constraints, with giving more scale over those post medium range. But the cost was related with the supply deficit over longer term. So the skill, even though we were improving for that setup, so remember it's a simplified system and simplified objective function. For that type, what matters was really longer term. So the medium range forecasts are improving the first month of the ESD forecast, but not much beyond that.
Okay.
So the April to July volumetric forecast was not, tremendously improved, so it wasn't very far from that.
Yes, I'm wondering whether the biggest improvement occurred in the first week or the second week or the week 3 or 4.
What matters the most?
So I'm wondering when does the biggest improvement occur in the first month? Is it in the first week, second week, or like week 3 or 4?
The medium range is helping a lot with the first 7 days that we saw.
Oh, first 7 days, okay.
Right, but there is a most here in the first couple of days, and then it starts decreasing. So this is at the daily time scale. When you start looking at aggregated period, this is actually going for a longer period. So it really depends what the objective functions or the constraints are going to look at. So it also depends on the reservoir capacity. If it's a very small capacity and what matters is daily flow, well, the scale that's going to matter is just the first couple of days. Yeah. If you start having a bigger capacity, you start looking at aggregated values, and then your medium range forecasts are going to have scale for aggregated values over the 2 weeks.
Okay, thank you.
Sure, thank you.
Okay, thank you very much, Nathalie. Are there any more questions? Otherwise, I thank you very much for a very interesting talk and all the people listening as well. And the next seminar will be in 27th of September by Massimiliano Staffa. So you're very welcome then as well to that seminar. So thank you for attending.
Thank you.
Thank you. Bye.